So, one of the functions of the skeletal system is movement, as we've already discussed. Now, it's not actually the bones that are providing the movement, it's obviously the muscles. The muscles provide the force and provide the power for the body to move around, but they can only do so if they're attached to bones, because those are the solid things, they're the framework inside our bodies. So it's fair to say that bones produce movement because they're sites of attachment for muscles, and that's the kind of thing you'd answer in part 1 of the first question in your scene test. Now, if we're going to try and explain how the skeleton's suited to that, how the skeleton is suited to movement or locomotion, the first thing we need to talk about is what a lever system is and what the different components are. Now, there are only 3 components of a lever system, and we talk about them and you see them in everyday occurrence. We've just got to formalize them so that when we move on to them all, a little bit more technical stuff, you know exactly what we're talking about. So if I can take you back to the playground and to a seesaw, this is a classic lever system which we can learn the different components of a lever, and then we can apply it to the human body. So what we have in the middle here of the bar along the middle is something called the fulcrum, which is just a basic fancy term for a pivot. It's the thing that the long line balances on, or the seesaw, the top of the seesaw balances on, and we have things on either end. So let's put a child at the end. Now this child at the end is a weight pushing down. Okay, and we call that the resistance. The resistance. And finally, at the other side, we have parent who's pushing down on the seesaw, on the end of the seesaw, and we call that effort. That is effort. So those are the 3 things involved in a lever system. There is effort, there is a pivot, and there's a resistance or weight. Those are the only 3 things that you need to concern yourself with a lever system. Now these 3 things could be put in different ways, and that's how we get different levers. But before we move on to the human body, it's very important that you understand those 3 concepts, those 3 words, and we can refer to those words with the first letter of what they stand for. So when I talk about R, I'm talking about resistance. When I'm talking about F, I'm talking about the fulcrum. When I'm talking about E, I'm talking about effort. Simple as that. So once you know the 3 components of a lever, you can then look at the different types or different classifications of lever system. And again, there are 3 classifications of lever system, and they are basically called first order lever system, second order lever system, and third order lever system. And it's very easy to remember which is which, and it's based on whichever component of a lever system is in the middle of the other 2. Now, me verbally explaining that will probably send you into a bit of a spin, but basically we can remember it by saying 1, 2, 3 F R E. 1, 2, 3 F R E. And all that means is, for a first order lever, the fulcrum has to be in the middle. For a second order lever, the resistance has to be in the middle. And for a third order lever, the effort has to be in the middle. So let's draw the seesaw that we had in the previous video. we have the resistance on this side, and we have the effort on this side, and the fulcrum in the middle. It's, when I say in the middle, it's placed between the resistance and the effort. The fulcrum is here in the middle of those two. So therefore, if the fulcrum is in the middle, it's called a first order lever. Okay, so let's say that we have a lever system like this. Here would be the fulcrum, and what we're going to do is lift this end up, so this would be the effort, and let's say we had a weight here pushing down, and this would be the resistance. So a little bit like opening a tin of paint, or even I don't know, a wheelbarrow. Forgive the crudity of the drawing. So if this was a wheelbarrow, there's a fulcrum, there's the wheel, that's the pivot, there's the resistance, i.e. the weight that you're lifting, and here is the effort where you are holding it up. Now the fact is that the resistance is in the middle, and hopefully doesn't take you a genius to work it out, but the resistance is in the middle of the fulcrum and the effort. So in this sense, this would be a second order lever because the resistance is in the middle. Hopefully you're getting that. Now, for a third order lever, the effort is in the middle. So let's just have a look at something like this. Something similar, that there's a fulcrum. Let's say there's a weight on this side, a weight, and let's say that the effort is being applied here. So the effort is being applied there. Now you can see that the effort is in the middle of the fulcrum and the resistance, and in doing so we can name that the third order lever because the effort is in the middle. So very easy to remember, there are three orders, which just means classifications or types. Three orders of lever, first, second and third, and it depends which component of the lever system is in the middle. If the fulcrum is in the middle, it's a first order lever. If it's if the resistance is in the middle, it's a second order lever, and if it's a third order lever, then the effort is in the middle. Now in terms of the human body, an example of each would be, so for the first order lever, let's consider this as the spine, the top of the spine, and let's consider this, forgive the crudity of the drawing, there's somebody's head, and what we have is a muscle that comes down the back of your neck there, which helps to rotate your head up and down, i.e. nod. So this would be the effort. The fulcrum for your head would be the top of the spine, and the resistance, i.e. the weight, would be the front of your head. Oh, that's meant to be an R. The resistance would be the front of your head. So you can see that the fulcrum would be the top of the spine, the effort would be the muscle at the back, which the name escapes me at this point in time, and then the resistance is the head that pushes down. So that would be one example from the human body for first order lever, and there aren't all that many, to be honest, from what I've read. A second order lever, if you think about somebody on their tiptoes, so here's somebody's foot, and there's the lower leg going up from here like that. So this would be a sort of shin in your calf area. Obviously the weight of your body is pushing down through your heel, essentially. Although it's off the floor, this would be the resistance. Then obviously your tiptoes would be the fulcrum, but the muscles involved would be down the back of the calf, and they would attach to the sort of heel of your foot, the calcaneus, and so they would be, this is what would be lifting your foot up into the air, or the back of your foot up into the air. And so you can see that the resistance is in the middle, and so this would be an example of a second order lever. So there's your toes, there's the pivot, the fulcrum, there's your heel in the air, but the body weight's coming down through your heel. But the muscle involved is the muscles around the back of your calf, such as your gastrocnemius and soleus, and that's what would be the effort. In terms of a third order lever, the effort is in the middle. So if I think a lot of your joints are third order levers, and I'm led to believe this is the most common lever system in the body. So if this is your humerus, this is your upper arm, and this would be your lower arm, then what happens is your biceps brachii, if I can draw it, attaches to your lower arm from your shoulder area, and so this would be your hand here, let's say picking up a ball of some kind. So the resistance would be the weight, or the dumbbell, or whatever you're lifting. The pivot or fulcrum would be your elbow joint, and the effort is actually the site of attachment for your biceps, which is where people go wrong. People think that the fulcrum is sort of in the middle, and whatever you lifting is there. It makes sense that the biceps pulling up on your forearm. You know, do it right now as you sort of listening to my voice. Your elbow is actually further away from your hand than the actual point of the attachment from your bicep, and it's that allows the effort to be applied in between the fulcrum and the resistance. So here we've got a bicep curl as an example of a third order lever. So hopefully that's useful, hopefully that's clear and explanatory. 3 classifications of lever system with an example of each. So you know what the components of a lever are, you know the 3 different classifications of a lever. Now what we need to explain is, so what? What do levers do for us? Why are they important? And how can they be applied in real life? Well, the first sort of application that I'd like to explain is something called a power lever. A power lever. So if we go back to the sort of traditional lever system which I started with in the previous slide, we have a resistance over here, we have the fulcrum in the middle, and we have effort being applied at the other end. Hopefully you can work out that that is a first class lever, because 1, 2, 3 FRE, F is the first, and therefore it's a first order lever. We're going to look at why this is important. Now, before you all start screaming, I can't do maths, I hate maths, I'm going to, go and commit suicide, that kind of thing. It's something that once you've got it, it should be extremely simple, and hopefully I can take you there. I'm going to give you a bit of an equation, and then I'm going to explain it, so don't panic. And the equation is, D is going to stand for distance. The distance of the effort times by the effort is the same as the distance from the resistance times resistance. Now I know that you're probably thinking, what the hell is this guy on about? Well, really it's relatively straightforward. So here, the distance of the effort, which is going to be this distance here from the fulcrum to the effort. That's going to be, I'm going to make this up, I'm going to make it up as 2 meters. So 2 meters times by the effort itself, and we're going to work that out. So I'm not going to tell you that straight away, is the same as the distance of the resistance. So I'm going to say that's also 2 meters by the resistance itself, and I'm going to say that that is 10 kilograms. 10 kilograms. So 2 times question mark, 2 times something, is the same as 2 times 10. So 2 times 10 over here, hopefully you're shouting out 20. So over here, 2 times something must equal 20. Now hopefully you're thinking 2 times 10 equals 20. So what implication does that have? Well, this distance and this distance is the same, and this is 10 kilograms. So if we put in 10 kilograms of effort, that means if we push down with 10 kilograms of effort on, or force, on this side of the lever, then we are putting enough effort to balance this lever system out. Wow, I hear you say, well, that's nothing new. Well, look what happens if I extend this lever arm. So this side is longer than this side, and I'm going to extend it to 4 meters. Now my question to you is, how much effort do you need to put down on this lever arm in order to lift this 10 kilogram weight? You can pause it and answer it yourself and see whether you get the right answer, or you can let it run and I'll just explain it straight away. So we go through the same procedure in terms of the equation. So the distance from the effort is 4 meters. From the fulcrum to the effort is 4 meters. We don't know the effort itself, that's what we're trying to work out. But that times this mystery figure is the same as 2, so distance of the distance of the resistance is still 2, and the actual resistance itself is 10. So all I'm doing is plugging in the figures there. So to expand that, 4 times something, I'm sure the mathematicians might give it X or Y or whatever, but I'm just going to give it question mark. 4 times something equals 2 times 10. So 4 times something equals, what's 2 times 10? Is 20. Now, although you're probably seeing the answer straight away, a lot of you, it is not always, the figures aren't always that easy. I'm using easy figures, and so you're probably saying 4 times 5 is 20, which is easy to see. But if you don't have a perfectly round number or an easily manageable number, how can we work it out? What in these figures allows us to work out that if we didn't know 4 times 5 is 20? Well, if we take the total sum from this side and we divide it by 4 on this side, we get 5. So what does that mean? Well, it means that over here, when we put effort on this thing at 2 meters away, we need to put 10 kilograms of effort. Since the lever arm has been extended, so we've doubled the length of the lever arm, what have we done to the effort? 10 to 5. We've halved it. So if we double the length of the lever arm, we half the amount of effort. So for 5 kilograms of effort to be put in, we're able to lift 10 kilograms of weight. Now that is one of the benefits of having levers in our body. They are said to be a mechanical advantage. We're able to lift lots of weight with a minimum amount of force. So they're energy efficient. We don't have to put much energy in to doing stuff, and they're all around us all the time. We're using those all the time, opening tins of paint, for example. Anything that we need to lift with a minimum amount of force, like a car jack. We're lifting cars by just turning a certain small rotary thing. However, they don't give us very much movement. So the actual distance that this thing will travel is very limited. Very, very limited. And it doesn't provide much speed at all. But like I said, in summary, these are power levers, and they are present in the human body. We are able to lift things for a minimum amount of effort. However, they are the less frequent lever system in our body. What we tend to do is use this in terms of our environment to our advantage. So ever since we've been evolving from the chimp days, we've used our environment to our mechanical advantage. So we use things like tweezers, like screwdrivers, like wheelbarrows to help us to manipulate force and provide movement, which will allow us to lift weights that we wouldn't usually do. So that is the function of a power lever. It's basically to move more weight for a minimum amount of force, but at the detriment of movement and speed. In terms of your exam, if I were you, I would use very easily manageable numbers, very similar to the ones that I've used. So you don't rely on your maths brain in the exam. You can the principle is that if you double the effort arm, you reduce the amount of effort you have to put in. So you'll not be surprised to know that a speed lever is useful because it provides speed. The last lever, which was a power lever, was able to lift weights with a minimum amount of effort. This is actually the flip side of things. Here we have to use quite a lot of effort, but we're able to create a lot of speed and a lot of movement. And speed levers are what's called a mechanical disadvantage. They provide lots of speed, they also provide lots of movement. So these give us a big range of movement, but they require more effort than is actually being asked of them. So they actually require more effort to move them, which may surprise you that these speed levers are far more common in the human body than power levers. Speed is at a precedent because we want to move fast. If we're being chased by that T-Rex, we need to be able to move fast. If we want to throw a spear to kill something, we need to be able to move fast, and that's where our limbs become speed levers. But they are at the detriment of power. We're not superhuman machines. We're not able to lift vast weights, which is why we use the environment to do that. but we are very fast, and we are able to create speed. So let's have a look at the mathematics involved in that. Let's say we have a pivot there, and we have the moment arm there, and this time we're going to have a different type of lever. So we've obviously got the fulcrum here, and we've got the resistance over here. What we're actually going to do is look to provide the effort there. Now you could potentially, if you take a step back, this is a little bit like a catapult. If we can get this arm flying across here, you can see the different movement it has. It has a massive range of movement, and if we can create that force, it's going to fling this brick a heck of a mile away. That's the difference between a speed lever and a power lever. You can see the movement, you can see the speed that we could generate, and therefore that would be propelled quite far. So let's talk numbers. We're going to say that this distance here is 8 meters. 8 meters. We're also going to say, for argument's sake, that this is 50 kilograms. 50 kilograms. So the distance of the resistance times resistance is the same as the distance of the effort times effort. So the distance of the resistance is 8 meters. The actual resistance is 50 kilograms. Now, the effort is going to be halfway. We're going to say that the distance from this fulcrum to the effort applied is going to be 4 meters. No, let's change it. Let's go 2 meters. 2 meters. So the distance from the fulcrum to the effort is 2 meters. What we don't know is how much effort is needed to provide that force. So let's go through the maths. 8 times 50 is, I hear you shouting me, yep, that's right, 400. Well done. 400 is equal to 2 times question mark. Well, it doesn't take a genius. Again, I'm using figures that are highly manipulable. Is that a word? Anyway, it should be easy to see. 400 equals 2 times something. I think my 9-year-old can get that, and hopefully you will do too. 2 times 200, so 400 equals 2 times 200. That's the maths. Let's have a look at how it plays out. 200 kilograms of effort. So hopefully that brings it home for you that we are at a mechanical disadvantage when we're talking about speed levers, because we're having to put in 200 kilograms of effort in order to move 50 kilograms of weight. That's quadrupling the size of effort. So if you can see, like we did in the last video, we doubled the distance and we halved the amount, we doubled the distance and we halved the amount of effort to put in, whereas in this case we've reduced the distance by a quarter, in fact by 3/4, and we've actually times it by 4. Essentially we're having to use 4 times more energy or effort than is the resistance or the weight. Okay, so they're really a mechanical disadvantage. We have to use more effort in order to move less weight, but they provide lots of speed. This projectile, this thing here, would be moving very fast by the time it got up there, and it also provides a larger range of movement. So to summarize, you've got all you need to know to sort of target the movement function on the skeleton muscle scene test part 2. Explain how the skeletal system is suited to the function of movement. Well, they're suited to the function of movement because they're able to provide levers and lever systems. And if you want to answer that question, you can go into what a lever is, what are the three components of a lever, what are three classifications of a lever, and you can go into speed and power levers, mechanical advantages and mechanical disadvantages. I hope that is clear. Please use it to help you learn, and we can do things in class to help you remember. Good luck.